Good afternoon. Today we'll start chapter number 3, that is transducer elements and intermediate elements. Now, transducer elements convert the input physical variable to usable form. In most cases, it is in the form of an electrical signal. The main advantages of getting an electrical signal as output are the following. First, inertia and friction effects are absent, unlike in transducers with mechanical outputs. Second, amplification can be obtained with relative ease. Third, indication or recording, especially at a distance, is greatly facilitated. The transducers would be discussed according to the classification, analog or digital types of transducers. In the former case, with the variation of input, there is continuous variation of output, while in the latter case, the output is of digital or discrete type. The following types of analog transducers would be described. First, electromechanical types comprising potentiometric resistance type, inductance, capacitive, piezoelectric, resistance, strain gauge, ionization, and mechanoelectronic types. Second, optoelectrical transducers comprising photoemissive, photoconductive, and photovoltaic types. Digital transducers would be discussed under the following heads: frequency generating types, digital encoder types. Now, this is the figure 4.1 scheme for measurement using electromechanical transducer. First, input or physical variable to be measured, that is input is given to the primary sensor. Then that primary sensor converts that input into mechanical displacement or strain. It is that mechanical displacement or strain is fed to the electromechanical transducer, and we are getting electrical output. Therefore, these three figures, so figure 4.2 A, B, and C, they are showing some transducers or conversion of input parameters to mechanical displacement. First of all, cantilever beam is there. Here, this elastic beam is there. If here you will apply the force, then we are getting the displacement. Similarly, this is fixed beam. If we will apply pressure to this elastic diaphragm, we are getting displacement, that is this diaphragm is going to displace, and this displacement is fed to the electromechanical transducer, and we are getting the electrical output. Similarly, this is primary sensor or temperature input by metallic strip. If we will hit one end of the strip, then what will happen? Depending upon the coefficient of expansion of these two strips, here two strips are there, that's why it is written here bimetallic strip. Depending upon the coefficient of linear expansion, these strips either they will bend in upward direction or they will bend in downward direction. Then next, analog transducers. First is electromechanical types. In such transducers, an electrical output is produced due to an input of mechanical displacement or strain. The mechanical displacement or strain input in turn may be produced by a primary sensor due to the input physical variable, which may be pressure, flow, etc. Figure 3.1 shows the scheme for measurement using an electromechanical transducer. Some of the primary sensors used for measurement of force, pressure, and temperature are shown in figure 3.2. Means earlier water figure we have seen. In each case, the input physical variable results in a displacement of an elastic member. In figure 3.2a, the force applied results in a displacement of the elastic member. In figure 3.2b, an elastic diaphragm converts pressure input into deflection or displacement. Similarly, a bimetallic strip of brass and invar alloys gets deflected due to change of temperature due to the difference in coefficient of linear expansion of the two materials. In each case, an electromechanical transducer may be employed to convert the displacement into an electrical signal that can be related to the force, pressure, or temperature input desired. Since displacement or motion is an input to an electromechanical transducer, this may be treated as a basic parameter derivable from several types of physical inputs. The transducer discussed here are also known as motion transducers. The following factors have to be kept in mind while considering the selection of motion transducers for a given application. First, magnitude of motion, whether the transducer is meant for measuring small, medium, or large motions. Second, type of input-output relation, whether the output is proportional to displacement motion, its rate of change with time with velocity or rate of change of velocity with acceleration. Static and dynamic characteristics, whether the transducer can measure static or dynamic or both types of displacements. Fourth, attachment or proximity type, whether the transducer has to be attached to the moving object or kept in close proximity to it. And fifth, self-generating or external power source type, whether a power output is needed to energize the transducer or the same is generated due to the input motion itself within the transducer. Now we will see potentiometric resistance type transducer. A wire wound potentiometer may be used as a transducer for converting mechanical displacement to an electrical output. This may be of linear or angular type as shown in figure 4.3. The motion of the object changes the effective resistance and hence the voltage output E naught between points B and C. Thus, the output voltage appears as shown in figure 4.3 and is directly proportional to the dynamic displacement of the moving object. Therefore, this is potentiometric resistance transducer. See that when this resistor or this it will be moved towards left or towards right, then there will be change in output voltage here. This change in output voltage it is shown here in sinusoidal. This is known as sinusoidal wave. Therefore, the value of the potential between the points B and C at the starting position may be large compared to the change in the potential due to motion. Due to this, a display on a display element like an oscilloscope may not be possible and the signal may be taken off the screen. To bring the initial value of E naught to 0, a position resistor as shown in figure 3.4 is used. Setting at B can be adjusted to give E naught at 0 depending on the initial position of the moving point A. This figure 3.4 also shows a protection resistor which prevents the movable contacts of the potentiometer from burning off in case the resistors are so placed that there is a short circuit across the battery. Therefore, here protection resistor is there. Protection resistor means what? It is used so placed that there is short circuit that is to remove unwanted things to happen or to prohibit or to prevent short circuit to happen. We can use this protection resistor. Now next is inductive type transducers. In these types of transducers, the magnetic characteristics of an electric circuit change due to the motion of the object. These may be classified into two types. First, self-generating types in which A voltage signal is generated in the transducer because of relative motion of a conductor and a magnetic field. Electrodynamic, electromagnetic, and eddy current types of transducers belong to this category. Second, non-self-generating or external power source types of transducers in which an external source is needed to energize a coil or coils, the inductance of which would change due to the motion of the object. The following types of transducers belong to this category: attachment type inductance transducer, air gap type, LVDT type, and magnetostrictive type transducer. First is self-generating type. Figure 3.5 shows an electrodynamic transducer type of transducer. A coil wound on a hollow cylinder of non-magnetic material moves in the annular space of a fixed magnet. The voltage generated in the coil is proportional to the rate of change of flux and hence the velocity of the moving object. The coil cylinder has to be attached to the moving object and thus this is a contact or attachment type transducer. Figure 3.6 shows an electrodynamic transducer for measuring rotary motion. The coil moves in the annular space between a magnet and a soft iron core, generating a voltage in the coil. Therefore, this is electrodynamic transducer for linear motion. When this is the permanent magnet, this is the coil. See that a coil wound on a hollow cylinder of non-magnetic material. This non-magnetic material is there. On that material, coil is wound, and this is a permanent magnet. It is fixed. Therefore, if you will move this cylinder, what will happen? There will be rate of change of flux. That is voltage generated in the coil is proportional to the rate of change of flux and hence the velocity of the moving object. Whatever this output voltage generated is proportional to the velocity of the moving object, or whenever this will move, it will move with some velocity. Therefore, there will be flux induced. Different values of flux will be induced in this coil, and that flux will generate output voltage. Therefore, that output voltage depends on the rate of change of flux or the velocity of this cylinder. This is for linear motion. Next is for rotary motion. This is permanent magnet. This is soft iron core. Again, these coils are wound on this hollow cylinder. Now, when this hollow cylinder will try to rotate, what will happen? Depending upon the rotational velocity or RPM, revolution per minute, that flux, different values of the, or there will be rate of change of flux induced in the coil. And because of that rate of change of flux, output value of the output voltage induced will be different, or we are getting different output voltage for different speed of this soft iron of this hollow cylinder, and we are getting output voltage that is calibrated. Therefore, we are getting the speed or RPM of the corresponding object. This is electromagnetic transducers here. What is the difference between electromagnetic transducer? In electromagnetic transducer, here coil is wound on the permanent magnet, and this is the object which can move either towards right or left. This is eddy current transducer. Permanent magnet is there. This coil is mounted. This is ferromagnetic material is there, and it will move up and down. And therefore, figure 3.7 shows an electromagnetic transducer in which a voltage is induced in the coil when the magnetic flux about it is varied due to the motion of the object, which has to be for a ferromagnetic material. This is a proximity type velocity transducer and is linear only for small motions as the flux density changes due to the change in air gap. Now figure 3.8 shows an eddy current type transducer. A non-ferrous plate moves in a direction perpendicular to the lines of flux of a magnet. Eddy currents are generated in the plate. These are proportional to the velocity of the plate. These eddy currents set up a magnetic field in a direction opposing the magnetic field that creates them. The output voltage E0 of the coil shown in figure 3.8 is proportional to the rate of change of eddy current or the acceleration of the plate. Since the gap remains constant, the transducer has linear characteristics. Therefore, I will explain now. This is the permanent magnet north-south. Here coil is wound. Electric supply is given so that these magnetic flux lines will move from north to south and south to north like this. Now when this ferromagnetic material is placed in between these two magnets, what will happen? And when we will displace it up and down, these magnetic flux lines will cut. Magnetic flux lines will be cut off, and that magnetic flux is induced in this object or ferromagnetic material, and this induced flux or induced voltage or this is known as eddy current. This is known as eddy current. This it will oppose this original magnetic field. It will oppose this original magnetic field. And see here, these eddy currents set up a magnetic field in a direction opposing the magnetic field that creates them. The output voltage E0 of the coil shown in figure 3.8 is proportional to the rate of change of eddy current or the acceleration of the plate. Since the gap remains constant, the transducer has linear characteristics. Now next is non-self-generating types. An inductance transducer of attachment type is shown in figure 3.9a. The core made of high permeability steel is attached to the moving object. See that this is the core which is attached to the moving object. It is of high permeability steel. These are two windings, L1 and L2. The motion changes the length of the flux inserted in the coil. Therefore, when this core will move up and down, therefore, depending upon the portion of this core in front of the coils L1 and L2, there will be change in magnetic flux. Therefore, the motion changes the length of the core is inserted in the coil, and thus the inductance of the coil gets changed due to the change of reluctance of the magnetic flux path. When the core moves up and down, the inductance of one half increases. Therefore, if this core will move upward, inductance of L1 will increase, inductance of L2 will decrease, while that of other half decreases. The two inductances L1 L2 form the adjacent arms of the Wheatstone bridge. The bridge output is modulated as shown in figure 3.9c. The output is supplied to a phase sensitive demodulator which eliminates the carrier frequency and gives an output corresponding to the motion frequency. The value of the output voltage being proportional to the displacement, the carrier frequency is usually much higher compared to the motion frequency. Therefore, this is the carrier frequency and this is the graph is motion frequency. Now figure 3.10 shows a variable inductance transducer for measuring angular displacement or torsional motion. See that. This is a variable inductance transducer for rotary motion. One half of the core is made up of a magnetic material, while the other half of non-magnetic material. The one half is made up of magnetic material, other half non-magnetic material. The inductances of the two halves of the coil depend upon the amount of the magnetic material in their flux paths. Therefore, whatever the inductance is in the two coils, inductance induced in these two coils depends upon the this portion of this magnetic material in their path. Therefore, the associated circuit of the same is shown in figure 3.9b. See that this is the same associated circuit. both for linear and rotary motion. Now this is proximity type inductance transducer. In the variable inductance transducer as shown in figure, sorry, here 3.11, a small air gap in the magnetic flux path of an electromagnet is varied. The inductance of one coil increases while that of the other coil decreases, with the circuit being similar to that of other inductor transducer discussed. The output is proportional to the displacement of the object. Therefore, this is again two permanent magnets are there. The coils are wound. Therefore, electric supply is provided. This object is there. This object will move up and down. Therefore, depending upon the distance of that object from that windings or from the windings L1, L2, therefore that much maximum voltage will be induced in that respective coil. In linear variable differential transducer, now this is LVDT for linear motion type, LVDT for rotary motion type. Now I will explain first of all, this is the primary windings. This is the soft iron core. It can move up and down. These two are secondary windings, S1 and S2. Now the magnetic flux or the voltage induced in these two coils S1 and S2 will depend upon the amount of portion of the core in front of these two coils. That is, if this core will move up, voltage or that flux induced, voltage induced in the coil S1 will be more as compared to voltage induced in the coil S2. Therefore, I will just read it. A soft iron core provides the magnetic coupling between a primary coil and two secondary coils connected in series opposition. When the core is central and both secondaries are identical, S1, S2, the voltages across them are equal in magnitude. However, the output is zero as both the secondaries are in series opposition. As the core moves up and down, the induced voltage of one secondary coil increases while that of the other decreases. The output voltage, which is modulated, is the difference of the two. Since secondaries are in opposition, the associated circuit is similar to that discussed earlier. The output is proportional to the displacement of the iron core. The device is very sensitive and is linear over a wide range of motion. Therefore, this is LVDT for linear motion type. This is LVDT for rotary motion type. Again, same. This is the iron core. It can rotate, rotational motion. Two secondary windings are there, S1 and S2, and one primary winding. Now, when this core will rotate clockwise, therefore maximum portion of this iron core will be in front of the secondary winding S2. Therefore, maximum voltage will be induced in the secondary winding S2 as compared to S1. Similarly, if it will rotate anti-clockwise, this soft iron core, what will happen? Maximum portion of this soft iron core material will be in front of secondary coil S1, and therefore maximum voltage will be induced in the secondary coil S1. Next is magnetostrictive type. This is the magnetostrictive type. See that this is the coil which is wound on this magnetostrictive material. This is force applied. Magnetostrictive transducer shown in figure is based on the principle that magnetic permeability of the ferromagnetic material like nickel changes when the material is subjected to mechanical stress. Therefore, this magnetic permeability will change. If the force will be applied, there will be stress induced in this material depending upon the cross-sectional area of this material, and due to change in mechanical stress, there will be change in the voltage, output voltage. The magnetic permeability of Ni increases when the material is subjected to compression and decreases due to tension. Thus, the inductance of the coil would change due to compression or tension of the probe. The magnitude and frequency of the exciting current determines the coil inductance, and the change in the same can be measured. Such transducers can be used for measurement of force, motion, etc. These have high mechanical impedance and thus resonant frequency is high with a good dynamic response. However, these transducers need individual calibration due to the fact that these transducers depend on the change of a physical property of a material, which may differ. Now next is the capacitive type of transducer. See that these three different configurations are there. This is the maybe object, this is the capacitor, or and we can consider that this object is considered as A, another capacitor is considered as B. Therefore, here object acts as a one capacitor. Here object acts as a one capacitor. Therefore, this is a displacement sensitive transducer. Due to motion, there is change in the capacitance between two plates. Suitable circuitry is used to generate a voltage corresponding to the capacitance change. Therefore, this is the one plate is there. Therefore, if you will move, incline it towards right or towards left, this is another capacitor. Because of change in air gap between these two capacitors, because of bending of this object towards right or towards left, therefore there will be a capacitance change. Therefore, the capacitance C between two plates is given by C is equal to epsilon A divided by 3.6 pi d, where C is equal to capacitance in picofarad. A is the area of plates in centimeter square. D is distance between plates in centimeter. Epsilon is dielectric constant of the medium between the plates is equal to 1 for air. Then capacitance C between plates A and B may change due to the change of gap as shown in figure 4.15 or due to the change in area as shown in figure 4.16. As a result of motion of member A, figure 3.17 shows top view of an area change type capacitive transducer which can be used for measuring rotational motion. Therefore, you just see this 3.15, this figure indicates gap change type capacitive transducer. That is, if gap will change, voltage, output voltage will also change. Second figure is the area change type capacitive transducer. When this measured or the standard capacitor is acting as a cantilever beam, we can move it up and down. Now, because of this movement of cantilever beam with capacitor up and down, there will be change in capacitance between the two capacitors A and B. We are getting the output voltage. And third figure 3.17. Third figure 3.17 shows that area change type capacitive transducer for rotational motion. Therefore, this is the one plate A, another plate B. This A plate is in having rotational motion. Therefore, if I will rotate this or anyone will rotate this moving plate A, what will happen? Due to rotation, there will be change in capacitance between these two plates. And due to change in capacitance, therefore voltage, output voltage will get different. Now next is the strain gauge transducers. Strain gauge transducers are of two types. First is unbonded strain gauge and second is bonded strain gauge. Now we'll read first of all, or we'll see first of all unbonded strain gauge. In an unbonded strain gauge, a resistance wire is stretched between two frames, one being the moving frame and the other is fixed. as shown in figure. Typical dimensions of the wire are 25 mm length and 25 micrometer diameter. The fixture plates acts as springs between the two frames. The wires are under preload, which is greater than any compressive load expected. An input motion as shown in figure 3.18 would stretch wires 1 and 3 and reduce tensions in wires 2 and 4. Motion in the opposite direction does not reverse. The wires are connected in a Wheatstone bridge are as shown in figure 3.18b. With this type of transducer, one can measure very small motions of the order of 50 micrometer and very small forces. These transducers may be used to measure force, pressure, acceleration, etc. Bonded resistance strain gauges. Transducers having bonded resistance gauges are widely used for measurement of several physical variables like strain, force, torque, pressure, vibrations, etc. These gauges may be of metallic or semiconductor type materials and are in the form of a wire gauge about 25 micrometer diameter or thin metal foil or steel rods in case of semiconductor gauges as shown in figure 4.16. Sorry, 4.29. These gauges having paper or some other material backing and are cemented or bonded to the surface whose strain is to be measured as shown in figure 430. Once bonded, the gauges undergo the same strain as that of the member surface. These are very sensitive and when used with electronic equipment, strains as low as 10 to 7 may be measured. Now gauges made of copper nickel alloys have a range of 2 to 3 while semiconductor gauges have a range factors of 100 to 200. Gauge current is usually limited to 10 to 30 milliampere while depending on the test duration in order to prevent damage. Bakelite base gauges can withstand somewhat higher values of current. Care has to be taken while bonding the gauges. The surface of the member has to be roughly clean. Later, the adhesive must be applied and allowed to set according to manufacturer's instructions. Then the connecting pads are soldered with gauge and securely fixed to the member as shown in figure 4.30. Finally, the gauge continuity and insulation resistance are checked in the subsequent. The strain gauges shown in figure 4.29 are represented by rectangles with the longer side being along the length of the wire, foil or semiconductor. Therefore, this is the diagram of unbonded strain gauges. See that this is the fixed prime. The strain gauges are mounted on it. 1, 2, 3, 4. 1, 2, 3, 4. Now these are the types of strain gauges. This is the wire gauge. This is the foil gauge. This is semiconductor plug. Then strain gauge in bonded position. This is the bonding of the strain gauge. This diagram is very important. How to bond the strain gauge to the member surface. Therefore, this strain gauge may be fixed to this member surface and then This strain gauge or movement of the strain gauge may be calibrated in terms of voltage and again in terms of that rank in the competition. Now next is ionization transducer. This works on the principle of development of voltage across two electrodes placed in an ionized gas, the magnitude of which depends on the electrode spacing and state of balance, which can change due to the motion to be measured. The transducer consists of a glass tube containing gas under pressure. A DC voltage is developed across the internal electrodes A when the tube is subjected to an electric field due to external electrodes B connected to a radio frequency voltage source. The gas in the tube gets ionized, and the D voltage and the DC voltage produced depends on the electrode spacing being 0 at null position as shown in figure 3.21. The motion xi, this is the motion xi of the tube relative to the fixed external electrodes. This tube either it can move towards right or towards left. Where is the output voltage? The balance between the electrodes may also be changed as in figure 3.22 by changing either capacitance Ci or C2. C1 is in figure 3.22, therefore here C1 is in figure due to the motion Xi is to be measured. This produces an output voltage E naught. Therefore see that this is the gas chamber. Here gas is filled, these two electrodes are there, gap is kept. Therefore, what will happen when this voltage is supplied? Therefore, there will be movement of these two electrodes either towards right or towards left. Now next is the mechano-electronic transducer. This type of transducer, which is of electronic displacement type, depends on the principle that the plate current depends on the spacing between an anode and a cathode in a diode or a triode. Figure 1.3.2 shows Figure 3.23 shows a transducer consisting of an evacuated tube in which cathode C is fixed and the position of the anode A is varied by the input of motion Xi, which causes deformation of an elastic diaphragm, producing a change in plate current which can be measured. This can be used for measuring displacement, pressure, force, etc. Therefore, this is the elastic diaphragm, this is the cathode, this is the anode. The workspace or the job is connected to the anode so that it will move towards left or towards right. And because of this, what will happen? There will be a deformation of the elastic diaphragm, producing a change in plate current. Now next is the optoelectrical transducer. These transducers convert a light beam into an electrical signal by proper interruption of the signal by proper interruption of the light signal due to the motion input. The electrical signal produced can be related to the input. There are three types of photoelectric transducers. Photoemissive, photoconductive, and photovoltaic transducers. This is photoemissive transducer. In this type of transducer shown in figure 3.24, Light beam strikes a photoemissive cathode. See that this is the cathode. Light beam will fall or it will strike the photoemissive cathode which releases electrons. It is attracted by anode. These are attracted towards the anode producing a current I in the circuit. Therefore, electrons are attracted towards anode and it will produce a current I in the circuit. The cathode and anode are enclosed in an enclosure that is either evacuated or filled with an inert gas. This cathode and anode are enclosed in a chamber which is filled with an inert gas or it may be evacuated. Current I is seen to be proportional to the intensity of incident radiation. That intensity of current I is proportional to the intensity of incident radiation. The sensitivity depending on the wavelength of the radiation as well. The cathode is made up of silver that is oxidized and covered with a layer of an alkali metal like cesium or alternatively of an alkali metal combined with antimony. High gains are possible by using photomultiplier as shown in figure 3.25, wherein the number of electrons is increased. The emitted electrons from cathode C are accelerated by voltage E and focused upon an electrode the diode DS or D2, where each incident electron causes the emission of secondary electrons. The electrons from D get focused on D2. Finally, these are attracted by the anode A, producing current I. The number of stages may be more than those indicated. Therefore, you just here, this is the cathode. When light will strike, it will produce electrons. Therefore, this first of all electrons will get struck on this diode D1. Again, from diode D1, more number of electrons will be emitted. Again, they will fall on diode D2, and again from diode D2, these electrons are attracted by this anode. Now, next is the photoconductive transducer. A photoconductive material like lead sulfide and or INSB, indium antimonide, changes its resistance due to a change in the intensity of incident light. Thus, in a circuit of the type shown in figure 3.26, the current in the circuit would change due to a change in intensity of the incident light. The latter in turn can be changed by the motion to be measured. Therefore, this is the photovoltaic transducer. This type of transducer has a sandwich construction consisting of a metal base plate 3. This is the metal base plate 3, a semiconductor material layer 2, selenium, and a thin transparent metal layer 1. As shown in figure, a voltage output is generated due to incident light and can be suitably measured. Piezoelectric transducer. This is the piezoelectric transducer. See that this it is in thickness T. This operates on the principle that when a crystalline material like quartz or barium titanate is distorted, an electrical charge is produced. Therefore, when force is applied, the crystal will get distorted or it will get strained or stressed, and because of that, electrical charge E naught is getting produced. Now next is the digital transducers. The transducers described so far are analog ones. Their outputs varies continuously according to the input. In digital transducers, however, the output is discrete and may give frequency type output or digitally coded output of binary or some other type. The main advantages of digital transducers are use of digital computers along with transducers for data manipulation is made easier. Digital signals, pulse count frequency or sequences of digitally codes outputs are not independent on signal amplitudes and are thus easy to transmit without distortion and external noise. Increased accuracy in pulse count is possible. There are ergonomic advantages in presenting digital data. Digital transducers range from frequency domain or frequency generating types of transducers to digital encoders. Alternatively, an instrument may incorporate an analog transducer and an analog to digital converter, giving a digital output. Figure 3.29 shows such an arrangement. Therefore, physical variable, it is given to the analog transducer. Analog transducer produces analog signal. It is fed to the analog to digital converter, and from this analog to digital converter, we are getting digital output. Therefore, this one frequency domain transducer we will see. In these transducers, the output is in the form of pulses or sinusoidal waveforms, the frequency of which is a measure of the magnitude of the physical variable. Frequency can be measured by frequency or pulse counter. Three types of frequency domain transducers have been described: electromagnetic frequency domain transducer, optoelectrical frequency domain transducer, and vibrating string transducer. We will see this electromagnetic frequency domain transducer. See that this is a two-thread gear. This is permanent magnet. Coil is wound, and we are getting this digital output. How we are getting this digital output? This is a two-thread gear. When this gear will rotate, since this gear is having teeth, depending upon the distance between this teeth and this magnet, how the different values of output signal will get. This type of transducer can be used for speed measurement as shown in figure. The device consists of a permanent magnet or solenoid on the rotating shaft whose speed is to be measured. A gear of ferromagnetic material is attached. As such, as each gear tooth passes in front of the magnet, the gap length changes. This changes the flux density and the voltage pulse is induced in the coil. Pulse frequency equals speed n times the number of teeth t. The form of the output signal is shown in figure 3.30. Thus, pulse frequency is a measure of speed of rotation. Therefore, another two types of transducers we will see tomorrow. We will stop here. Thank you very much. Thank you. Hello. Okay, we'll